What's going on? It's Marty from CramBetter.com. If you want to follow along with the examples I'll be doing in this video, check out the video description to download the study guide. It's free to print or use on your tablet. We made it. We're talking trig sub. So what is trig sub? It's what it sounds like. It's when you do some kind of substitution, but using a trig function. What does that mean? Well, it means that you're going to eventually be doing some kind of trig integral. So I want to preface this before we go any further here. If you're still feeling a little bit rusty on trig integrals, definitely review that stuff. Make sure that you're solid on it because we need it in order to do trig substitution. So we're going to look at just a quick overview here. And the basic idea behind trig substitution is the following, okay? You're going to have a sum or difference of squares. That's really important. That's the first pattern that you're looking for. And it's going to be raised to some half power, okay? When I say half power, it could be like 3 halves. It could be 5 halves. I mean, it could be 1 half as well. It could be anything that is some half power, an odd number over 2, right? That's the power that you're looking for, okay? Why is it that we're going to do a trig substitution? Well, because we're going to use our Pythagorean identities to take our sums and differences of squares, break them into a single square, and then basically cancel out that half power. So we want to cancel the half power. That is the point. That's really the logic that you want to have underlying every single decision you make with trig sub. So how do we actually do it? Well, like I said, we're going to use our Pythagorean identities and we're looking for patterns. It's all just about patterns, which identity you choose. So here's some example integrals that you could run into. And then basically the way you read this table, you got the example, you have the sum or difference of squares that you want to use, and then the Pythagorean identity that goes along with it. Now, for me personally, when I do these, I actually start off with identifying the correct Pythagorean identity, right? So I want to make sure that I start there. And then from there, once I know which identity, everything else basically follows from the logic. Now, I'm showing you in the table the substitution that you're going to make based on the pattern. And if you want to memorize this table, you can do it. And again, you'll definitely save time if you do that, but only if you really understand the logic behind it. You got to understand why you're doing this, or else it's going to just be like a whole mess of random things, random facts when you get to the exam. And I don't want that to happen. I want to make sure that you understand what's happening here, okay? Now, these are the steps. You can look back at it for your reference. The one that I do want to really emphasize here, okay, this is the 4th step. You got to do a trig integral, okay? You're going to run into trig integrals as a step within these trig substitutions. That's the whole point of them, okay? So we're going to try a quick little example here. Hey, before we go any further, I just wanted to mention to you that what you're watching right now is a topic review from CramBetter.com. On our website, you'll find more stuff like this, as well as study guides and sets of practice exam questions for every topic in your course. So be sure to check it out. But for now, let's get back to it. So evaluate the following integral x cubed over square root of 1 minus x squared dx. So the first thing that we need to make sure that we're good with is, well, why is this a trig sub? Well, we have a square root, that's a 1/2 power, and we have a difference or a sum of squares. In this case, it's a difference of squares. So yeah, this is going to be a good candidate for a trig sub. So now what substitution do I use? Well, just think about your Pythagorean identities. You have a number minus a variable. I want my trig function to basically represent my variable. So I'm going to be thinking 1 minus sine squared of theta equals cosine squared of theta. That's the trig identity I'm going to try to get to, okay? If you look up here, that's that. You can see the form. You have a number minus a variable squared. That's the identity we use. We're going to look at the substitution. You can memorize it, but I want you to make sense of it. So here we go. So now how do I pick the right substitution? Well, I want to basically match this form. So I'm going to just say, you know what? I don't like the x right there. I want to use a trig identity. I'm going to use my Pythagorean identity. So I'm going to set x equal to sine of theta so I can get it to act like this, okay? So now when I do that, I have 1 minus x squared. And notice, no calculus quite yet. I'm just doing manipulations. And actually, I'll do it over here. 1 minus x squared. If I sub in, I get 1 minus sine squared of theta, and I can simplify that to cosine squared of theta. Now, why is that useful? Well, let's look at it in the context of the integral. If I come back over here and I do the substitution, I have x. Well, x is sine of theta. So this would be sine cubed of theta. On the bottom, I have root 1 minus x squared, but take a look what we just did. 1 minus x squared is 1 minus sine squared. 1 minus sine squared is cosine squared, and this is the beauty. This is what's so beautiful about this method. The square root and the square cancel. What I had before, this disgusting like root 1 minus x squared, I couldn't cancel anything. I couldn't simplify it. Now I can. That's what trig sub allows us to do. Now, one last thing, I kind of skipped over this detail just to really show you this simplification here. But the other thing you want to be aware of is the coefficients, right? There's a 1 right here. You need to make sure that whatever coefficient is on your sign, it's going to cancel. So you have 1 times sine of theta. If you square that out, you'll have the 1. That's fine. In this case, it didn't matter because it's just 1, so who cares? But that's why if you look at this table, I have it set up where I have like b squared minus a squared x squared. I have it set up in this way so that you know that you're compensating for those values. Now that's one way. The other way that you could do this, you could have the a over here. And this is actually how I often do it. Ax equals b sine theta. You could also do this kind of substitution. It's a little bit more straightforward and you get the exact same sort of thing. All right. And it would apply to the others. This would be ax equals b tangent theta, etc., right? Ax equals b secant theta. And what happens? Well, when I apply this, ax equals b sine theta, well, if I square it, take a look. The b squared is going to appear here, a b squared and the sine theta. I can factor that out, and I'll be able to use the Pythagorean identity that I want to use. That's the logic behind what's happening. You got to make sure you understand that so you can understand how to, well, get these questions right. Okay, now, haven't done any calculus yet. Now we're going to do the rest of the substitution. So if I have x equals sine of theta, I'm going to finish over here, do my calc part. I'll do dx. The derivative of sine is cosine, so dx equals cosine of theta, d theta. All right, great. So now I have that. Well, I'm just going to plug that in. This is cosine of theta, d theta, and I'm going to simplify this integral now. So I have integral of, this will be sine cubed on top. On the bottom, square root of cosine squared is cosine of theta. And then here I got cosine theta, d theta. So it's pretty nice. Okay. Once you get this idea, once you understand that everything stems back to just taking advantage of that Pythagorean identity, they're actually very straightforward substitutions to make. The hard part, and this is what I said earlier, it's the trig integral, right? The trig integrals suck. They're the worst part of this integration stuff that you do. But if you're good with it, if you've practiced it, it shouldn't give you any issues. So we have sine cubed of theta. So we have an odd power on sine. What do? Well, we want to pull out one of the signs. So we have an even power on sine. So we can use our Pythagorean identity. So we're going to have integral sine squared theta, and then sine of theta, d theta, right? That's our rule. We have an odd power on sine. We're going to use u equals cosine of theta. And the reason we do that is because, well, again, we have to do it that way, right? We have a sine theta that's kind of just hanging out. The only thing that we really ever can work with are even powers on sine and cosine, because we can use Pythagorean identities or reduction formulas. Now, in this case, we're going to use the Pythagorean identity because we want to have the cosine there, so that's the case. So, going ahead and do that. I'm going to plug in my identity. This will be 1 minus cosine squared of theta. This is sine of theta over here. Okay, this is good. If I go back, I have my u in mind. If I do du now, du equals negative sine of theta d theta. And I solve for sine theta d theta because that's what I see right there. I get negative du equals sine theta d theta. Again, just another method for substituting stuff in. You can always solve for d theta and plug in and cancel, but this can save you a little bit of time, okay? And now I'm going to plug in what I can. I'm going to sub everything in. So I have integral 1 minus u squared. Remember, cosine was my u, so I'm plugging that in. And then sine of theta, that's negative du, or sine theta d theta is negative du. So I'm going to distribute that negative. I'm going to write this as the integral of u squared minus 1 du. And we just do that integral really quickly. We get u cubed over 3 minus u plus c. We sub back in. Remember, our u was cosine. So this is going to be cosine cubed of theta over 3 minus cosine of theta. Now, that's all well and good, but the problem is our original answer was in terms of x. So we have to put this back in terms of x, and this is where the last part of trig sub comes in. It's really important. We have to make sure that we draw a right triangle so we can actually find our trig functions in terms of x. So I'm going to do that. Draw a nice little right triangle here. This is theta, and I just bring down the original substitution. The original substitution was x equals sine of theta. So I'm going to write that over here. X equals sine of theta. And I just draw a right triangle based on that. So sine is opposite over hypotenuse. This is going to be x over 1. If it helps you to write that, x over 1, do it like that. The missing side, we need that. That's going to be 1 minus x squared, square rooted. Nice little logic check. Whatever you get for that missing side should match what you had on the inside of your integral, on the inside of the root. Whether it's 1/2, 3/2, 5/2 power, it should match on the inside, okay? Which, that's good. It matches. So now we're going to do cosine cubed. Now, cosine of theta, I'm just going to write it over here separately. Cosine of theta is going to be adjacent over hypotenuse. That's just root 1 minus x squared. If I do cosine cubed of theta, okay, keep in mind, root 1 minus x squared, that's the same thing as 1 minus x squared to the 1/2 power. I can raise that to the third power, so I get 1 minus x squared to the 3/2, all right? Just multiply the exponents. Remember those exponent rules. So I take that, and I can plug it back in over here. This is going to be, all right, this is 1/3 times 1 minus x squared to the 3/2, and then cosine of theta, we know, we just found that, that was root 1 minus x squared, so minus the square root of 1 minus x squared plus c, and I am looking great, okay? So what's the big takeaway for trig sub? Most important part is making sure that you understand how to do the trig integral that comes about after you do the trig sub, but really to get there, you're looking for sums and differences of squares, and you're looking to apply a Pythagorean identity to take that sum or difference, reduce it to a single term, right, a single square, so you can cancel out that 1/2 power. How are you going to know to look for this? Look for odd powers over 2, right, half powers, 1/2, 3/2, 5/2, and sums or differences of squares raised to that. If you see that somewhere in your integral, it's a really good chance that you're going to be doing a trig sub. So get used to those patterns, be good with your trig integrals, and don't forget this little triangle thing at the end to make sure that you can get back to x from that theta situation that you have, okay? You put all that stuff together, you'll be fine with trig sub. If you want to pass your classes the easy way, head to CramBetter.com. We've got study guides, practice exam questions, and shorter, easier explanations for every topic in your class. So click the link in the video description, and I'll see you there.